Hey, hello, can everyone hear me? If anyone can hear me, just say something in the chat. And we should get a start soon. Hello to all the people that joined. I see a few extra people have joined. Yay, okay, I can be heard, that's wonderful. How's everyone's days been? It's been a good Wednesday afternoon. Okay, thanks Paris. I'll get a start on in about like a minute or so. Also, apologies in advance if there is like any background noise. It's a bit hard to stream at home, but what can we do? Okay, I'm just gonna get a start on, and before I start on anything, I'm just gonna say, just answer a few common questions that people tend to ask later on. First of which being, is this live stream recorded? It is. And it will be uploaded maybe about 25-30 minutes after this ends. I'm not sure about the inner workings of why YouTube takes so long to upload it afterwards, but it just takes that long. But it definitely will be uploaded later onto our YouTube channel. The other common question is, will these lecture slides be uploaded as well? And that is also true. Yep, we will upload these, but usually there's like a few errors when I'm like walking through, so like I'll just have to fix that up. It'll be out in maybe tomorrow or the day after, which is, I don't think it's too bad anyways, considering the fact that, correct me if I'm wrong, but the MATH2901 final exam is like situated towards the end of the exam block. So you guys have like heaps of time to study. But yeah, those are two common questions I usually get asked, so I'm just gonna quickly get them out of the way now, just in case anyone was wondering about that and didn't want to speak up. But yeah, okay, I think we can actually get a start on the actual content. And I'm just going to pick up right where Gordon left off in the first half. And that was talking about the weak law of large numbers. And it's going to be really important because I'm going to reference it in a few questions later on. But just letting everyone know that the weak law of large numbers is, if we've got a sequence of random independent variables, each with a mean mu, and usually you just say that x1 all the way up to xn is IID, right? And it's to some distribution, which I'll just call D, right? They're independently and identically distributed because they've all got mean mu and finite variance sigma squared. Yep. Then the sample mean will converge in probability to the true mean, right? That means the sample mean is going to converge in probability to the true mean. So as Gordon has written here, essentially this means that as we take larger sample sizes, our sample mean will more likely be closer to the true mean. And I think a good way of thinking about this is if you got like a box of balls, right? So here's my box, and it's got, I don't know, a few balls in it, right? There is a true average called mu of the average weight of these balls, right? It is whatever all these guys are divided by 6, so on, right? Average, right? But if you just take out one or two of these balls, like let's just say this guy and this guy, then you get a different mean. And I'm going to call this mean mu xn. I'll be a bit more specific, mu x2 because we've taken out 2 balls, and that's going to give some average, right? And it's not exactly this mu, right? Because we're obviously missing 4 balls. But if you keep increasing how many balls that you do measure, then eventually it will become this mu, right? Because that's the true mean, but you just don't have all that data yet, right? And that's exactly what's going on here. It's just, at this point in time, you've only got a finite set of data, but as you keep increasing and increasing, you eventually get to the true mean. That's a way I like to think about it, just intuitively. And then here we've got the strong law of large numbers, and it's just essentially the same idea. It's just instead of convergence and probability, which has got some like technical definition, we've got almost surely convergent, right? And these are just like technical aspects, right? I think the intuition stays the same with both of these concepts, okay? I will be using the weak law of large numbers later on, so just quickly wanted to go over that. So now to where I've started writing the slides, and this is just going to be applications of the central limit theorem. And this is the normal approximation to the binomial distribution. It just says that if you've got some binomially distributed random variable x, then you can, then this is the case, right? And I'll quickly remind everyone that the expected value of x equals to np, which could be considered as mu, and the variance of x equals to np 1 minus p. And you can think of that as sigma squared, right? So you could, in essence, sort of change this to be mu and this to be sigma, right? And then that can just be said as x minus mu over sigma approaches in distribution to the normal, standard normal distribution. Right here, we've just substituted in the values of, in our case, because we've got a binomial distribution. Mu here is np. Our standard deviation is the root of np 1 minus p. Right? So nothing too crazy. I've just substituted in values to the usual central limit theorem. Nothing really crazy. But it's kind of cool because what this is actually saying is that the binomial distribution is the discrete version of the normal distribution, right? Because as you keep getting more and more samples, they tend to behave almost the same, right? They're approximately equal, which is cool intuition to have. Yep, and I'm just going to quickly go through an example of when you would use this. Like it's all well and cool having this approximation, but when are we actually going to use it? And here's an example from the 2020 final in the MATH2801 paper. I'll quickly read it out. It says that 2 theatres compete for the business of 1,000 customers and assume that each customer chooses between the theatres independently. That means they're just like indifferent between the two. On any one day, they could choose one or the other. Let n denote the number of seats in each theatre. And here I'll just quickly add a note to say that n is the same for both theatres. Okay. The first part is asking us to use a binomial model to find a condition in terms of n, which will guarantee that the probability of a particular theatre turning away a customer is less than 1%. The next question is just asking us to explain how the binomial distribution can be approximated by a normal distribution. And the next question is saying by using the normal approximation, give an approximate value for n so that A is satisfied. Okay. I'm just going to tackle this in order. So I'm just going to go to the first question, A. And I think the hardest part of doing these stats questions is just setting up appropriate notation, right? It's really hard to just look at this and condense it down into information that you actually need to use, right? You've got 2 theatre companies and each have got 1,000 customers and n denotes the number of seats in each theatre. It's a lot of, I guess words, and you really need to be able to distill that into symbols so you can actually, do some maths on it. And so here's what I'm going to do is I'm going to say it's a lot at the moment, but I'm just going to say that X is the number of people in any particular theatre. And obviously in quotation marks, X is binomially distributed with 1,000 as N, because right, there's 1,000 customers, and a probability of 1/2. And that's the case because each customer is indifferent between the two options. So it's even, right? They could choose one or the other, so we're saying the probability is 1/2. Okay? And the condition states that we want, right, if I go back up to the question, we want the probability of a particular theatre turning away customer to be less than 1%, right? So if I was just to write this down, probability theatre turns away customer. And we want that specifically to be less than 1%, which I'm just going to write as 0.01, right? Each theatre hosts n amount of people, right? So we need the number of people actually going in, which is X for any particular theatre, to be greater than n, right? Because if there's more people trying to enter that theatre than is possible for that theatre to host, then we've got the case where the theatre will turn away that customer, right? And so that's what I've written here. We've got that the probability that X is greater than n is less than 0.01. Now from here, I'm just going to use the definition of, because we know X is binomially distributed, I'm just using the CDF and just manipulating it, and I get to this expression, which is a bit, actually really ugly, right? We've got the sum from X equals to n plus 1, all the way to 1,000, 1,000x times 1/2 to the power of x, 1 minus 1/2 to the power of 1,000 minus x, right? Which is, not the greatest expression, but this implies that I've just simplified this down. This is 1/2 to the power of 1,000 minus x, and this is 1/2 to the x. So you can just add the exponents and then bring that out right to the front because this is not indexed. And so that's where I get to here. And then I'm just going to conclude this. We can theoretically solve for n. That is, n is the smallest integer that satisfies this expression, right? And then that would be part A completed, because we have found an expression for n such that we can get that condition to be true. And here's a bit of a comment about why we're actually going to end up using this normal approximation instead of actually just trying to find n, is that solving for n in the above expression isn't really particularly easy. Like, I would look at this and I wouldn't know what to do, right? It's just, if you've got any ideas, that's good on you. I really just do not know how I would solve this. But that's okay, because we've got this normal approximation that's going to help us out, right? Because if we're talking about 1,000 customers, we only need to know approximately how many seats that we need. Not exactly, It's like big enough numbers, right? And so to solve part B, I'm just literally just going to repeat what the normal approximation is. It's that x minus np, which is, once again, this is just literally the central limit theorem. That's mu, that's sigma, and that approaches in distribution to normal 0, 1, right? I'm going to keep moving. Okay, and now I'm just going to quickly do part C, right? So just for everyone to recall, part C is by using the normal approximation, give an approximate value for n so that the condition obtained in A is satisfied. Okay? So this is part C. I'm just going to be using this formula and seeing how far I can go. NP in our case is the expected value, so that's 1,000 times 1/2, which equals to 500. Just write this in green. That's NP. And then the root of the variance is our sigma, which is equal to root NP 1 minus P. Okay, lovely. And then we're just going to enforce this condition. Probability that x is greater than n is less than 0.01. And that this is equivalent to this expression here, which might not be so obvious. So I'm just going to quickly explain how I got to this. And it's not so bad. Basically, you just start off with your expression, right? We know this is true. And anything inside this probability, you can kind of treat it as like a normal inequality / equation. So whatever you do to one side, you can do to the other. And so this is equivalent to the probability that x minus 500 is greater than n minus 500. And then that's equivalent to the probability that x minus 500 on the square root of 250 is greater than n minus 500 over the square root of 250. Right, that's all I've done. So not too difficult, hopefully. Hopefully that makes sense. And then from here, we can use the normal approximation because we're saying that this guy is approximately N01. So I'm just going to call it Z. And so now I've said that Z is greater than this expression on the right, where Z is normal 0, 1. So moving on. I omitted this from the question stem just purely because I didn't have space on the slides, but we were given this information as well. It says that the Qnorm, which means quantile, normal. And so you read this expression as the 99th percent quantile of the normal distribution, standard normal distribution, is 2.326. And then we're also told that the 90th quantile is 1.28 and the 95th quantile is 1.644, right? And here we just want a 1% probability. And so because the normal distribution is symmetric, the standard one, a 99th percentile here is the same as a 1% percentile. The number will just be flipped. So it really doesn't matter, right? And that's the same as 99%. Okay. So I want to be using this top result. So this 2.326. I'm not doing a 10%. I don't want it to be 10%. I don't want it to be 5%. I want it to be 1%, the chance. So I'll be using this quantile. And so that means the probability that Z is greater than 2.33 is approximately 0.99, same as 0.01. And then n minus 500 over root 250 equals to 2.33. And then you can just solve for n, and that means n is approximately 537. And so to conclude, each theatre should have at least 537 seats if we want the condition of part A to be satisfied. Which is a bit of a long question, so if anyone's got any questions, give some time. Okay, if not, I'm just going to keep going. I think this really highlights the reason why we want to, use these normal approximations. Because if we go back to our original equation, it was a bit dastardly. Like I don't know how to solve this. And so that's exactly why the question was just saying, hey, can you find an expression? And of course we can. And this highlights the difference, or more so the reasoning of why we want to use an approximation instead of just trying to solve for everything exactly. Okay. Now moving on. We've got Lutskys Theorem, and it just says that if we've got some sequence of random variables converging to x in distribution, how did you get to that expression? Yes, part A, sure. We can quickly go over that. Which expression exactly? Is it this one here? I guess I didn't explain this one, but this is just using the binomial distribution, right? like if I was to just distill this down and I was asking first line. Okay, yes. Okay, so this one. So basically, if you want x to be greater than n, and this is not equal to, right? Then x has to equal to n plus 1 all the way up to 1,000, right? And then this is just the definition of the PMF, right? So the probability mass function of a binomial distribution equals to, I think I'm just going to choose big N here, x. That might actually be confusing. I'll say big T, why not? T choose x, and then this is the probability of x, 1 minus p to the power of t minus x, right? That's the PMF. And so if we want this to be greater than n, we have to consider the fact that PMF has to be n plus 1 plus PMF of n plus 2 plus the PMF of n plus 3 all the way up to, yeah, I think you got it. Yeah, please let me know if I skip a few steps, because what's obvious to me might not be obvious for everyone. But yeah, here I've just like abused the probability mass function to get out this expression. Okay, perfect. So going back to Lutskys Theorem, here we've just got a sequence of random variables, and I'll quickly remind everyone what a random variable really is. It's just a function, right? From the sample space to the real numbers. So if this is confusing to you, you're like, what actually is a random variable, of like a sequence of random variables? Just think of it as a sequence of functions, right? We've got this first function, and then this next function, and it keeps going on and on and on. And we want to talk about how this function behaves as this sequence tends to infinity, right? And then we've got another sequence of random variables, and they both converge different ways, probability and in distribution. And this just says that the sum of these sequences approaches in distribution to essentially their limits, right? Because this is saying xn approaches in distribution to some guy x, and then yn approaches in probability to some constant c, right? It's just saying you can add these guys or you can multiply these guys, and then they just become like their limit counterparts. So then this becomes x plus c, right? Because this guy approaches x, this guy approaches c, so it's then x plus c, and then here it's c times x. Okay, hopefully that makes sense. And I'll go through an example of when you can use Lutskys Theorem. Suppose that x1, x2 converges in distribution to normal 0, 1, so the standard normal distribution. And suppose that n times y of n is binomially distributed n with parameter n and 1/2. And we're being asked what are the eliminating distributions of xn plus yn and xn times yn. Okay, so that's the question we're being asked. And it's a bit difficult at first because we've got one sequence, but it's not immediately obvious where our second sequence is, right? I'm like telling you guys you can use Lutskys Theorem, but if you go back up to it, it's like we've got two sequences here. So it almost seems like we don't really have that case here. But we do, because we can do a little bit of some funny business and convert this into two sequences. And I'll show you how to do that. And specifically, we want a sequence for this guy, right? Because we've got a sequence for the x, but we need a sequence for the y's, right? And so I want everyone to recall that any binomial distribution is just a sum of n IID Bernoulli random variables, right? So any binomial distribution, you can convert it into this guy. So it's just the sum from I equals 1 to n Bernoulli p. And then obviously I can just rearrange this to say that yn equals 1 over n, I equals 1 to n Bernoulli p. Right? And so this means that yn approaches in probability. So this is where the weak law of large numbers comes into play. Yn will then approach in probability to the expected value of Bernoulli p, which just equals to p. I'll quickly write this down here. Expected value equals to p, and in our case that's just a half. So that's how I get this number. And then we've got our two sequences, right? We've got this guy's approaching to 1/2, and the other guy is approaching to normal 0, 1. So therefore, xn plus yn approaches in distribution to 1/2, 1. And I'll make this a bit more obvious, right? Xn plus yn approaches in distribution to 1/2 plus normal 0, 1. Right, and remember, adding a constant onto the variance doesn't change the variance. So this guy stays the same. But adding a constant to the expected value does change the expected value by that much. So therefore this is equal to n 1/2, 1. Next, it's the same concept here. We've got 1/2 times n 0, 1. If you're multiplying the standard the variance by something, to take it back in, you have to take the square of it, right? So for the expected value, you can just multiply it in, but we've got 0 here, so it doesn't change. To pull this guy in, you need to square it. So then this becomes 1/4 times 1, and that's how I get this number. Does that make sense? Definitely the trickiest part with this example is recalling this fact, that any binomial distribution is in fact a sum of n IID Bernoulli random variables. So you can use the weak law of large numbers. Okay. Moving on, we're going to use the delta method now. And so once again, we're going to have a sequence of random variables such that root n times yn minus theta over sigma is distributed by n 0, 1. Suppose that g is differentiable in the neighborhood of theta, and g dash theta is not equal to 0. Neighborhood is just a technical term. It just means like around that point, you can differentiate it. Right? I think they'll never ask you a question where this does not hold. Right? It's more that this wouldn't hold, rather than the fact it's not differentiable in a neighborhood of theta. So you can kind of just like forget about this, right? They're not going to test you on you knowing what exactly this means. But the delta method says that root n times gy of n minus g theta approaches in distribution to 0 sigma squared g dash theta all squared. And it's really easy to look at something that's pretty abstract. You look at this and you're like, what is this actually saying? Why would I want to know this? What is the point of this? And the delta method is a good way to solve an issue that Gordon brought up in the first half of the seminar. And that is, we know the distribution of a random variable, but we want to know the distribution of a function of it, right? Rarely do you talk about a random variable x and you're just like, what is its behavior, right? You want to consider a function of it. Right, because in the real world, like if you're looking at population dynamics, right, like the population could have one distribution, which I'll just call D, but you're not just looking at the population, you're looking about maybe like the birth rate, which would be a function of the current population, or you're looking at the infection rate, which I'll just call I of X, right? These are all functions of a random variable. And so this is why this method is so powerful, because in reality, all you need is your function to be differentiable in a neighborhood, and you just need to know the underlying distribution to sort of approximate how this function's distribution will behave in the long run. Okay, so here's an example from the 2015 paper. This is question 2c. It says let xi be, so I equals 1 to 2, whatever. This is once again a sequence of random variables, and they're all independent Bernoulli p random variables. And we're just letting yn equal its average. Okay, I equals 1 to n of xi. We want to show that as n approaches infinity, root of n, yn minus p approaches in distribution to this guy. Then for the next part, show that for p not equal to a half, as n approaches infinity, the random variable yn times 1 minus yn satisfies this really long expression that I will not be saying out loud because there is absolutely 0 point. I think if you just look at this question, it can be really daunting because you look at this and you're like, how on earth am I going to, prove any of this? There's so many variables, there's so many expressions, there's so much things going on. And I think it's just really important to take a step back and just apply what you know and just hope that everything works out, right? So we'll take it slow. We're just going to do the first part, I. So showing that this is that. And if you ever see something like root n, yn minus p, approaches in distribution to something normal, then your first short thought should be, oh, central limit theorem, right? That's where your first thought should be. Central limit theorem, central limit theorem, central limit theorem. And this is exactly what's going to happen. We're just going to use the central limit theorem, right? And this is what the central limit theorem states, if anyone's forgotten. It means that yn minus mu times root n approaches in distribution the normal 0 sigma squared. In our case, because we've got xi is Bernoulli p, this means that mu, which equals the expected value of xi, just equals to p, and sigma squared, which equals to the variance of xi, equals to p, 1 minus p. Okay? So that's exactly this. And this guy is exactly that guy. So all we had to do was substitute this in. The hardest part in solving this question was realizing what the mean was of a Bernoulli random variable and what the variance was. Okay? I think they give you a table anyways, like what's the expected value of all these common distributions. So you don't need to necessarily know this, but you just need to remember that the central limit theorem exists, and the giveaway is that it's something that looks like that. Okay? So that's part I done. And now we need to do part double I, which looks a lot more difficult. But I've given everyone a hint because I've said that this is just an example of the delta method, right? So if we go back up to the delta method, we need some function g, which is differentiable at some point, and we need that the derivative at that point is not equal to 0, and we can do this, right? And it's not immediately obvious that's what you will get, but I hope everyone can realize, so if I go all the way to here, if you say that g of x equals to x 1 minus x, and you differentiate this guy, you get that g dash of x equals to 1 minus x plus x times minus 1, which equals to 1 minus 2 of x, which looks awfully familiar to this, right? And I think that's the giveaway to use the delta method. You've got a function here, and you can recognize its derivative being in here. And then, therefore, sirens should go off. Yeah, I'm going to use the delta method. And so that's exactly what I'm going to do. I'm going to let our differentiable function be g of x equals to x times 1 minus x, then g dash of x equals to 1 minus 2x. We note that g dash of a half, right? So when p equals to a half, this guy does in fact equal to 0. And remember, that was a condition that we weren't allowed to have in the delta method. So we can't have p equaling to a half. So just after assuming this, plug in everything into our delta method, which is this guy right here. You get that root n. So just making this clear, g of x equals to x times 1 minus x. Then you can substitute in y of n. So g y of n equals to, sorry, no root here, yn 1 minus y of n. And that's why I've got this here. And then g of theta, so in our case, we're looking at probability. So theta in our case is P. Right? So theta could just be anything, but we're saying it's P. Then that's P times 1 minus P, and that approaches in distribution to this guy, which is actually not really a bad question. You look at this and you're like, I've got no idea where to begin. There's so many things going on. And it's just trying to remember two facts: central limit theorem and the delta method. And you can get this question out really easily. Okay. I think that ties up everything with convergence and the central limit theorem, which is where we left off with Gordon. So now I'm going to talk about statistical inference. And I think for most people who did the course, everyone kind of despises statistical inference, which I don't know why. I think it's really interesting. It just depends on how you look at it. Because it can be really dry and there's just a bunch of numbers all the time and it's a lot of formulas. But it is really powerful, and it's the most tangible thing that you can immediately use from this course. It's really hard to use the delta method in everyday life. But stuff like statistical inference, there's heaps of things on the news that are talking about like p-values and hypothesis tests. And just having some idea of this just immediately makes you more equipped to understand so many more contexts. Yeah. Oh, Paris has got a question. With the part I, this part I don't get how that is the central limit theorem. Do you say that the central limit theorem is like this? Is this what you usually think to be the central limit theorem? I don't get how that is the central limit theorem. Isn't central limit theorem usually divided by sigma squared? Wait, okay, so you do agree that this is how it should look like? The thing I'm circling right now. With a square root of n at the bottom. Square root of n should be at the top here, right? And then that's the central limit theorem. This is exactly this, right? These guys are absolutely equivalent because you can multiply out the sigma to both sides in essence and say that yn minus mu approaches in distribution to sigma normal 0, 1, right? And then if we want to multiply a constant to some distribution, you just think about the expected value and the variance. The expected value is just going to be 0 times sigma, which just still stays as 0. And if you want to change the variance, then it becomes sigma squared times by 1, right? And then that becomes sigma squared here. And so these guys are absolutely equivalent formulations. This one here and this one here. Does that sort of make sense? This fact here might not be immediately obvious. Just remember that a times the variance of some distribution, some random variable, equals to the variance of a squared times x, which is what I'm doing here. And then a times the expected value of x just equals to the expected value of ax. And that's exactly what happens. Yeah, no worries, Paris. Just ask as many questions as you like. Okay, perfect. So statistical inference time. Hopefully I tried to do some sort of motivation so you guys can get a little interested in this, because it is frankly sort of boring. But we can make some headway on it. So here's the definition of an estimator. If we've got some sort of sample, So here this notation can be a bit confusing because usually when we've got this, we're talking about a sequence, which I guess in this sense it still is a sequence. But when we have like these brackets here, we usually mean it's a sample. So we've drawn out numbers from something that we know to be a distribution, and we're saying that it's distributed by this guy, which takes in some parameter theta. And we say that an estimator of theta, denoted by theta hat, is any real valued function of the sample. And that's it. That's literally the definition of an estimator. You take in this sample and it's just a function and it'll spit back out to a number. Right? Takes in all your data. And you guys have been working with estimators for pretty much the entire time you've been learning maths, right? Estimators like the average is an estimator, right? Because you take in the entire sample and you spit back out a function. Well, sorry, the mean is a function, and it takes in a sample and spits back out a number. The median is an example of an estimator. The mode is just take in the data, spit back out a number, and that's an estimator. And it's usually talking about a parameter of the distribution in question. So usually the average is trying to estimate the expected value, so mu, and I don't know, the in-sample variance, Sx, usually tries to estimate the variance. Or the standard deviation can do that. It's the same business. Okay, so here I've just unpacked the definition a little better. X1 to xn denotes a sample of a random variable. X has this probability density function with some parameter, and we call the estimator, it's just simply a function. Okay, here's properties of an estimator. The estimator is a random variable, right? And remember, random variable is just something from a sample space to the real numbers. And that's exactly what's happening. You're taking some samples and spitting back out a real number. So therefore, this guy is a random variable. Subsequently, an estimator has its own probabilities distribution and can be computed from the distribution of the sample. Here's just an open question to you guys just to think about, is think of an estimator which has a different distribution from the sample data. This doesn't mean too much, it's just something to think about. They can be wildly different. Okay, and here's bias of estimators, and the wonderful thing about this definition is that it's really intuitive. Right? Usually you say something is biased if you're like tipping your hands on the scale. So the expected value of theta hat minus the real value should be 0, and we call that an unbiased estimator. Right? Because an estimator which has this property means that it is coinciding to what we should expect it to be. Right? So we're not tipping the scales one way or the other. It's exactly what we think it should be, and therefore we call it unbiased. And so here's an example. Suppose x is a discrete random variable with probability mass function p of x, and that the space of x is finite. Say it's, I don't know, denoted by this guy, d, it's a1 up to am. And suppose that x1 to xn are samples taken from x such that each sample is independent of the other. We want to show that the estimator of the probability mass function, denoted by this expression here, is indeed unbiased. And then from there, we're going to compute the variance and see if we can do anything. And here's just some notation. This is just called the indicator function. Just means that if xi equals to aj, then this evaluates to 1. Otherwise, it's going to be 0. It's just saying true or false. Is this statement true? Yep. If this statement is false, I'm going to assign it a 0. If you do any computer science or any coding courses, we use this concept all the time. If something's true, we give it a 1. If something's false, we give it a 0. Here I've just explained the best way to solve these kind of questions about unbiased or biased estimators is just take the expression given and just slap the expected value and see how far you can simplify things down. So this is what I've got here, right? Because that's my expression, and I'm just going to slap the expected value on it and then simplify as far as possible. So here it is. 1 on n is a constant, so I can pull that out, and then I can pull the expected value in. And so I've got this. From here, the next question that arises is that what is indeed the expected value of the indicator function, right? And I think you're probably taught this, but I think it's better just to think about it intuitively so you don't forget, is that a Bernoulli distribution kind of measures the same thing as an indicator function. It's like, if something succeeds, then I'm just going to assign it a value. If something doesn't succeed, I won't assign it a value. So this indicator function is really just a Bernoulli random variable, right? And so that's exactly what I've said here. Therefore, remember, the expected value of a Bernoulli random variable is just p, and so that's the probability that xi equals to ai. So I've just gone through the steps. That's what we've talked about here, Bernoulli. Then the next step, that the probability that xi equals to aj is just the probability of aj. And then, sorry, not the probability, the PMF, the probability mass function. Right, the probability mass function evaluated at aj is this guy. Right, so that's how I got to this step. And then here, there's no more index of I. So really, I'm just adding this n times. Add n times. And then divide by n. Yep, and then like adding n times is just multiplying by n, then dividing by n. So we've not really done anything, and we've just got this Paj. And so to conclude, you just apply the definition of bias. This is what we're trying to estimate. So that was like our theta, and this is our theta hat, expected value of theta hat, sorry. And we get that this is just 0. And so the estimator of the PMF is unbiased. Here for the variance, I'm just going to skip over this really quickly. Once again, if you want to pull out 1 over n, it just becomes squared. So here, you square things, just write 2. And then the variance of Bernoulli random variable is once again p1 minus p. There's no more index of n here, so you're multiplying by n, then dividing by n squared, and so you're just left with n in the denominator. Okay. This was in the 2020 assignment, and it just asks, we've got 2, we've got 1, I'll just go through it. We've got x1, x2, all the way up to xn, they're a random sample, they're IID, each with mean mu x and variance that's finite. And the usual estimator for mu is the definition that you're usually aware of for averages, right? You just add up all the samples together and then divide by the number of samples. And here we're assuming that n is greater than 3, and a student investigates an alternative estimator for mu by ignoring x minus x n minus 1 and xn and multiplying x1 by 3. So here this student is just basically saying, I don't like these values, I don't want to deal with them anymore, and to make up for the fact that I'm just not using them, I will, I'll weight x1 by 3. So in essence, I've done x1 plus x1 plus x1, which equals to 3x1, and that accommodates for the fact that I've omitted xn minus 1 and xn. Right? And now we've got this new estimator, which is exactly the usual definition of this formula, except that we're now ignoring these two values and multiplying this 3 to the first sample. And here's pretty cool is the fact that this estimator is indeed also unbiased, right? Which intuitively doesn't make sense, because obviously if like you apply the literal definition of bias, you're essentially applying a bias to x1. Mathematically, it still means that this estimator is unbiased, right? And so I'm going to quickly demonstrate how to do that. Once again, I'm going to slap the expected value onto this and then compute the bias. So here it is. Once again, the expected value is always linear, so I can just pull things out as I wish. So this 1 over n I can pull out because it's just a constant. This 3, I'm going to push this guy in here, so distribute it across, and then I'm going to distribute expected value into the sum. Then each of them are IID mu, so they're identically and independently distributed, so they all have the same average, which is mu. And then here is just applying the sum. You can just re-index this to be the form of I equals 1 to n minus 3. Right, this exact same thing. If you want to move this guy down by 1, then you're going to pull this guy down by 1 as well. And so therefore, I've got n minus 3 terms, and so I'm multiplying this by n minus 3, and then just doing the algebra, you get to mu, right? And so therefore, the bias is mu minus mu, which does indeed equal to 0. And so we can get away with saying that x tilde n is an unbiased estimator. Okay, here's the mean squared error, because we're being asked to calculate the mean squared error, but I've not really gone through it. But the mean squared error is just this formula. And we usually don't want to work with this formula unless we absolutely have to. So I'll write that down, unless we have to. It's just best to work with this guy. This guy's going to be a lot more easier to work with. It's just going to be the bias squared plus the variance. And to prove that this guy and this guy are equivalent, it takes like 2 or 3 steps. It's not too bad. So you could probably just remember this and just simplify as far as possible to get to here. We remember that the bias is just 0, so we just need to calculate the variance for the mean squared error. And so once again, I'm just going to slap the variance onto our estimator and see how far we can go. Here, if we want to take out a constant, we just have to square it. Here, if I'm going to push this variance inside, I also have to square this guy, and so on. Usually, and I didn't say this here, but you have to note that x1, x2, xn are all IID. Otherwise, that this expression is just false. If this assumption doesn't hold, the fact that they're not IID, then you have to get some weird covariance terms, like something like 2 cov I like less than j, or something like, don't remember exactly, but usually don't get asked a question about it, so it's not too important. But if this wasn't the case, then you'd have this extra term here, and this wouldn't be so straightforward of a calculation. Okay, then once again, just go through the algebra, not too bad, and you get to here. The mean squared error, sigma squared on n squared times 6 plus n. Okay, then we're going to go to part 3, which I will quickly go through again. We want to show that this limit of the mean squared error also approaches 0 for this estimator, which is not too bad. We know what our mean squared error is. We calculated it in part 2. We just want to apply the limit. This guy is going to get really, really large, and this guy is constant, and this guy is also going to get really large. So this is just effectively 0. Right? And then that's it. We've proved what we needed to do, that the mean squared error approaches 0. Okay, now part 4 is that I think it's a good time to just think about this question and saying what it's really meaning. It's that we could have, if we really wanted to, at this point, have used this definition for an average. Sorry, there's no 3 in front of here, but it just goes up to xn minus 1. xn minus 2, sorry. All the way divided by n. And this is unbiased and MSE approaches 0. So a question you could ask is, well, if this is an equally valid formula to estimate the average of a distribution, why do we use the usual kind? Why is this guy, never taught to us? Why is it always just x1 all the way up to xn? What's going on here? Why have we just learned this and not this? And the reason why is because, which I'll get to in part 5, but here also going to show that both of these guys, actually sorry, it is part 4. Yeah, it's just saying here that both of these limits also approach 0. So the usual estimator approaches 0, and this unbiased estimator also approaches 0. But we need to know which one would be considered a better estimate for mu. And the way we do that is we can compute the variance. Right? The variance of the unbiased estimator is going to be sigma squared on n, which is less than or equal to 6 sigma squared over n squared plus sigma squared over n, which equals the variance of our unbiased estimator. Which means that although all these properties hold for this this weird formula, it is indeed still better to use the one that we were taught, simply because the variance is tinier. And it's just better to have a smaller variance. It just means there's less volatility in the results. Right? And so therefore, the usual estimator is indeed better, is indeed the better estimator. Okay? Does anyone have questions on that? There was a lot of parts. Okay, if not, I'm just going to keep going. And so here's some asymptotic properties of the estimator. We say that an estimator is consistent if, as n approaches infinity, the estimator in probability converges to the actual, parameter. And we say it's asymptotically normal if the estimator divided by the standard error approaches in distribution to the standard normal distribution. And the standard error, if anyone's forgotten, it's right here. I believe it's just, actually might be wrong. I believe it's just the standard deviation over root n. Question mark, question mark? I forget. I definitely go through an example of when we use standard error. So I will be, using this. And so we'll know for sure. But anyways, we're going to keep going, and we're going to talk about a really, really important distribution used all the time in inference, and that's the student t distribution. And we say a random variable t is said to have a t distribution with degree of freedom nu if its probability density function is this monstrous creature. Very rarely do you have to directly work with this. And if you think you have to directly work with this, there's probably a way better method. So avoid this if possible. You definitely do not want to work directly with this function, because dealing with gamma functions in general is just, tough. But I pose this question: why should you care? Why is this an important distribution in inference? Why does it pop up all the time? Is to jog everyone's memory, this is the central limit theorem, right? You've got sigma over root n is normally distributed 0, 1. But usually, in fact, you don't really have this on hand. You don't have the standard deviation. It's never the case that you don't know the mean, or actually you know both of these guys, but you don't know the standard deviation, right? So usually you have to replace it by something like the in-sample variance, right? Sx squared, which is just this formula, which I believe is just the normal standard deviation formula squared, right? And that's usually what you do with the data. And so if you replace this guy with sigma, then you get, it's actually indeed Tn minus 1 distributed, right? And that's why this guy pops up all the time, is because for real data, you're not really working with, hypotheticals of saying like, we do have sigma, but you usually calculate that with the data already given. And so therefore you've got this t-distribution. Okay. I'm going to quickly go through what a confidence interval is, and then we're going to take around a 5-minute break. I'll quickly go over these 2 slides, and then we'll take a break, and then we'll resume soon. But a confidence interval is, well, what's it actually solving? And I'll present the problem, and it's that, suppose that we do have a random variable of interest x with density. It's this guy. Could be whatever. And it's got some parameter theta, and theta is unknown. And we want to estimate theta by statistic, right? So some function on our sample, and we want to estimate this guy. Okay. When the sample is drawn, it is unlikely that the value of the estimator is the true value of the parameter. And in fact, if theta hat has a continuous distribution, then the probability that indeed our test statistic does actually equal our parameter, it's always 0. And this is the case for any continuous distribution, right? So we're saying that the probability that the test statistic that we do create is truly the actual value of our sample is 0. So how can we create any meaningful discussion of estimators and distributions if this issue is always glaring us right in the face? How do we solve this? Right? And instead, we don't look at exactly this guy. We kind of talk about an interval around theta hat, right? We don't want to talk about this guy directly because the probability it is actually theta is 0, right? It's not possible. So what is needed is an estimate of the error of the estimation by how much did our estimate miss the true value. And that's the purpose of the confidence interval. Okay? And so I'm going to leave this slide up here, and then I'm going to I think we'll restart at 4:05. Just grab some water, stretch your legs, I don't know, move around from the computer for a bit, and I'll speak to you guys shortly. Also, if anyone has any questions, just feel free to ask me in this time period. Okay, I think I'm going to resume now and just talk about confidence intervals, just give the technical definition, and that is, if we let x1 up to xn be a sample on a random variable, where x has this probability density function, and we're letting some number between 0 and 1 be specified. And we're going to have two statistics, L and U, that act on the sample. And we're going to say that LU is a 1 minus alpha 100% confidence interval if 1 minus alpha equals the probability that theta is indeed in this interval, right? So if we specified alpha to be 0.01, then we're saying that the probability that our parameter of interest is within this interval equals to 1 minus 0.01, which equals to 99%. So we can say that we're 99% sure that the true value of theta is within this interval, right? Once again, if you get what a statistic is, it's just saying that it's just two functions on the sample, L and U. And we're going to make them return a value, and then we're going to construct an interval based on these values. And so the probability that theta is within this is 1 minus alpha, and we're going to call 1 minus alpha the confidence coefficient. Hopefully that all makes sense. Okay, and then we're going to talk about confidence intervals for a normal random sample, and that's let x1 be to xn be a sample from n sigma mu squared. Then a 100 1 minus alpha % confidence interval for mu is this guy, which is I remember when I first looked at this when I did the course, and I was like, what is going on here? And I really didn't want to know it, but in reality, it's literally just a formula. Like, this guy here is just the in-sample mean. Like, everyone knows what this is. It's just mu, the sum over total over, I'll just say number. Tn minus 1 is just the t distribution with n minus 1 degrees of freedom. S is just the in-sample variance. Better yet, standard deviation, because it's not squared. So this is just the standard deviation. Right? And these are things you can directly work out from data given to you. You can work this guy out. You can work this guy out. You can definitely work out whatever root n is. And so what's left is, what on earth is going on here? And what this is saying is that t, subscript n minus 1, 1 minus alpha on 2, is the 1 minus alpha on 2 quantile of the t n minus 1 distribution. So if we have a large sample, say n approaches infinity, and we want to know the 95th percentile, we can write in R absolute, and this is the quantile t distribution, 0.95, and then here's the degrees of freedom, which would be infinity. And then this will give you back out a number, so you can work out whatever this guy is, right? So don't be too alarmed if you're looking at this and you're like, this is really complicated. Nothing crazy is going on. You can work this guy out with R, you can work this guy out with R, you can work this guy out just from the data given to you. So it's not too bad. And so here's a question, and we've got the density of the log normal random variable x is this guy. So I'm going to write this as x log norm. We're saying it's just dependent on sigma. So we know what mu is, but we don't know what sigma squared is. This is our parameter of interest, theta. And it's got this distribution with theta greater than 0 is just some constant. And I'm going to assert for you guys that sigma hat is an estimator of sigma. Okay? And we need to compute the distribution of the estimator, sigma hat squared, on sigma squared, and compute using the data set below, which it can be any data set, doesn't really matter. Construct a two-sided 95% confidence interval for sigma squared. Okay? So let's just go through the motions of this, which is it's not too bad, but there's definitely like a lot of, manipulation to get out this quantity. And I'll start this off by, you guys might not be aware, but the log of this is just normal mu sigma squared. I think. Yeah, we know mu to be 0. I should say that. We are assuming mu equals to 0. So we know that this is the case, right? And you can prove this. It's just a change of variable formula that was covered in the first half of the seminar. This is not too bad to prove, okay? So I'm just going to go through this, and it's just like making observations, okay? We've got that ln x is normally distributed 0 sigma squared, right? And now we want to standardize this, right? So if we've got, I say this is like kind of tricky. So say that ln x over mu is n01. Because we can work from this guy directly. We can pull out sigma squared by just pulling out sigma. So we can say that ln x is distributed sigma, that's a terrible n, n01, right? Because if you want to reverse this operation, you have to square this guy, put him back in, and that's exactly the same step. And then you can divide out by sigma, and you get this expression. Okay. Here's something that is always tested, so you should definitely remember it, is that the sum of n random variables squared and normal random variables squared is a chi-squared distribution with n degrees of freedom, right? So if you sum up all these standard normal distributions, it's chi-squared. Okay, and the chi-squared distribution is just a special case of the gamma distribution. This is another fact that might not be known to everyone, but it is indeed the case, right? Chi-squared is just gamma n over 2. And so if some random variable x is gamma alpha b, then x on n is this. And this is somewhere in the lecture notes. I don't think we directly prove this, because I think it might be a little tricky. But you definitely can. Yep, okay. And so just collating all this data, you get that this guy has to be gamma n over 2, 2 over n. And that's a lot to take in, so I'm actually just going to go through these steps one more time. Just going to add a page here and just go through it. I'm going to start off, I think everyone was fine with this step. ln of x over sigma is distributed by n01, right? Now, remember, we're working with this definition. So I'm going to have this here, sigma hat equals to root 1 over n sum I equals 1 to n. ln x I squared. Just going to make sure that's correct. Okay, cool. Cool. We've got this guy. I feel as if this should be a squared here. Or I might be wrong. Oh, okay. I'm being silly. Yeah. Okay, so this is the expression we want to get to, which is this guy on the right hand side here. Okay, so that's what I'm working towards, and I know that ln x, so this is definitely squared. This is a typo. It should be squared here. And we're saying that ln x over sigma, which is exactly this guy in the bracket, right here, we're saying that this is z, which is the standard normal curve, right? And we also know that the square of the sum of n of the square of the standard normal curves is chi-squared distributed, right? So we know that 1 over n, that's a terrible color. One moment. We know that this is then 1 over n chi-squared n distributed. That expression, which I'm just going to call L for convenience. L is then distributed by that, and then L is also distributed by chi-squared, which is just gamma n over 2. Then we can use this fact here, and we can say that L is therefore distributed by gamma. The alpha doesn't change, right? It's just the beta that's changing here, and we just divide that by n, so we get n over 2 over n. And that's exactly this. This is a bit tricky, and there's like a lot of things going on. Does anyone have questions? It's definitely a lot of facts to remember. Okay, just going to move on. Okay, from there, we know that it's gamma n over 2 over n, right? So we can use this distribution to get some numbers in. If we want a confidence interval, why is chi-squared useful? I think chi-squared, chi-squared, I forget how it's pronounced. In general, I mean, like, where does it arise? Yeah, that is a good question. I'm not sure, to be honest, where this guy comes up. It just so happens that heaps of times that you're looking at functions, right, with a square term, right? So this is some random variable x, and you're squaring it. And obviously, with some random variables x, you can just approximate it by normal 0, 1. And so the square of this guy, and you're just summing them all up, just so happens it's this distribution. I think the reason why chi-squared is so useful is because a lot of the times you've got normal distributions and you're squaring them, because you square everything as a function, right? It's like the first, nonlinear function that we learn in school is the squared function. It just pops up everywhere. If you want to model anything, you're squaring something, right? I don't know how to justify why we're summing all of these guys up. It just so happens that we do, which is a bit unfortunate. Hopefully that's like some sort of answer. Okay, I think for here, we can work this out. We want to get a two-sided 95% confidence interval. So the top side is going to be the 97.5% quantile, and there's going to be the the 2.5% quantile, right? And then this total equals 5%. Just using the confidence interval formula. Remember, we've got an alpha on 2. So divide by 2, and then add it where appropriate. And so here I'm just saying that this is the quantile, and then we get this expression here, and that should be our confidence interval. It's our confidence interval. Okay? And you can work this out just with R. You can say that X is some vector of some numbers, so this is the data set. We want n to be the length of that data set. And then we're just going to have our estimator be that formula that we found right above here. That's our formula for the estimator. And so I've just coded this up into R, and then that's going to be just a formula. And here's the 2.5% quantile for the gamma distribution with n on 2 and 2 on n. This is going to give some number out. This is going to give some number out. And then we can work out the lower bound by just using this formula here. I've calculated lower and higher based on this guy and this guy. I usually get thrown off by all these distributions, especially because a lot of them are not expressed in elementary terms, but instead by weird integrals and gammas. They seem a bit non-intuitive. Yeah, for sure. For sure. I just think mainly because even if you look at the PDF of the normal distribution, it's not immediately obvious how it's it arises. You've got a pi in there for some reason. You've got a whole bunch of stuff. I think a lot of this stuff is really crazy because you assume so little and then you get really, really difficult and non-intuitive distributions arising from it. It just goes to show that although this is graspable and there is some intuitive aspects of it, sometimes you just got to do the nitty-gritty and get the maths working. But yeah, definitely it's a bit difficult. If you were to going back to this question, you could, if you really wanted to, calculate the PDF of this guy. And I guarantee you, it just wouldn't work out. Well, if you did get it to work out, it'd just take ages. So you want to, where possible, not deal with the PDF because they're non-intuitive. If you have to work out with integrals, it's just going to be really, really hard. So it's just best to have these guys memorized, like the fact that you can standardize this normal distribution. This is a thing, and then that this is a thing, and that this is a thing, rather than dealing with really, really difficult integrals. It's just a trade-off. Do you want to memorize, 3-4 statements, or do you want to have to deal with like pages long integrals, right? There is a trade-off there, and I do agree with you. It's not at all intuitive when you work with the PDFs. Okay, I think that's that. You can definitely use this code, right? If you when we upload the slides, just put in a data set here. Just suppose that it is indeed what we've assumed it to be, and you can get the confidence interval out. It'll be exactly right. Okay. Now we're going to talk about likelihood estimators. So we're going to let x1 up to xn be observations from the PDF f, where f of x is some distribution with parameter theta. Okay. The likelihood function is just the product of all of the because obviously the PDF is just a function, so you can just substitute it in a value and you get some number out. You get some number out and you just multiply those together, and therefore you get this guy. And at the end of it, you should get some function based on theta, right? Because theta is just some parameter. It could be a number, could not be. We're just going to let it be a parameter. And we're going to say the log likelihood function is just this likelihood estimator, and we're just going to slap a log on it. And this directly follows, right? If you got ln of a product, say ai, this just gets converted into a sum. Right? That's all that's going on. This follows directly. Okay? And here's the really important thing, is to note that the maximum likelihood estimate of theta is the choice that the estimator equals theta that maximizes this function, this estimator function over our parameter. Okay? And the fact is that you can maximize not only this guy to get out this value, but you can also maximize the log of the likelihood. And these maxes coincide. So it's often better just to work with the log of the likelihood rather than the likelihood itself, right? Because it's better to work with a sum rather than a product. Because I feel as if we just have more experience working with sums than products. So this is just easier to work with. Okay. And so I'm just going back to this example. I said beforehand that this guy was an estimator, and you may or may not believe me, but we'll go ahead now and prove that it is indeed an estimator, and it's actually a maximum likelihood estimator. Okay? And so what we want to start off with is just applying the definition. right? We've got nowhere to go here, right? We've given the PDF, and now it's just saying calculate the MLE. So we have to just applying the definition of the likelihood estimator. It's this product, and then we're going to denote the log likelihood estimator with the log of this estimator, and it's just that expression. Here's what's important: maximizing the likelihood function is equivalent to maximizing the log likelihood function. Okay. And so here's just, it's a lot of algebra, but it's not too difficult to work with here. I'm just directly applying what I can do. If you apply log to this terrible expression, I equals 1 to n, 1 over xi sigma root 2 pi. I'm just going to make this bracket, I'm not writing that down. Then this just becomes a sum, and then this guy will become log of 1 over something, and then log and e are inverses, so you're just going to get minus something else, which is what we've got here. I've just skipped a few steps and got into there, and then we can, everything here is just of the form xi to the power of -1, and so we can just pull that out, just using the usual properties of the logarithm, and we can keep going, and we get to this expression right at the end. And now is an opportune time to work out the derivative. Remember, when we want to maximize a function, we work out the derivative, we find the stationary point, and then solve for it. Okay, so we're going to compute the derivative, and then we're going to let it become a stationary point, right? Calculating this derivative in respect to sigma means that this guy just gets wiped away, and I believe this guy just gets wiped away, right? Because these guys aren't functions of sigma. So you get left with this, and then we're going to let this guy equal to 0, and then just by rearranging, we get what we needed to prove, right? But this isn't completely like finished. You also just have to confirm that this actually is a maximum, right? It's not enough just working out the stationary point and saying, yeah, I'm sure it is a maximum. You just have to go ahead and confirm that that is indeed the case. So we're going to check that the stationary point is a maximum. We're going to confirm that the second derivative is less than 0. So just work out the second derivative, you get this expression, and then we're checking it's less than 0 at that particular point. So we're going to substitute this guy in, which looks a lot more difficult than it actually is. Everything just works out beautifully. And you get that this is just an expression which is negative times something that's always positive. So therefore, this is less than 0. And so we've confirmed that this is indeed a maximum likelihood estimator. Okay. So some properties of the maximum likelihood estimator is that it's consistent. So this guy approaches in probability to theta. And then equivalence is that g, so some nice function, which I'll maybe quickly explain what that means, is the MLE of g of theta as well. And a nice function just means, like, you can just think of any function really. It just means you could find counterexamples if you wanted to, like some pathological function, which this wouldn't be the case. But for most purposes, this is just fine. You can just say that g of theta is the MLE of g of theta. And here's another thing, asymptotic normality. We can say that the estimator minus the parameter divided by the standard error approaches in distribution to normal 0, 1. And I'm going to quickly explain how to prove this, or where you'd find this. And it seems that I've forgotten to include some information. So this is called the Fisher information matrix, which I'll explain somewhere here. Yeah, I've got these slides the wrong way around. So IN theta is just this, which looks disastrous, but I promise it's not too difficult. But also, we've got this here, which is really important, and it always comes up. This will always be tested, I feel, that the standard error is approximately equal to 1 over this Fisher information, right? We're told that IN theta equals to n over sigma squared. So just using that fact, we get that the standard error, the approximate standard error, is approximately 1 over the root of that guy, which equals to just going through the motions, theta hat over root n. Okay? Thus, we can just use asymptotic normality, right? We've got theta over root n, which is what that guy is here, approaches in distribution to normal 0, 1. And then how do I get to here is that theta hat minus theta approaches in distribution to root n over theta. Is that right? Yes. Yep, I believe that's right. Normal 0, 1. No, I've got that the wrong way around. Sorry. This should be theta over root n. Then you can just pull in the standard deviation. This gets squared. So this equals to normal 0 theta squared over n. And then once again, you can slap over the theta and get the theta hat. The expected value will change, but not the variance here. So this will be normal theta squared over n. And that's how I've got this expression. Okay, wonderful. Sorry for the placement of this slide. This should have been. I changed this last minute because I thought I'm talking about asymptotic normality here, but it was all the way over here before, which is a bit weird. And then I changed it, not realizing that I had indeed needed to explain what this was. But it's fine, we'll quickly go over it. The definition of the Fisher score and the Fisher information. So this is just the log likelihood function. So it's just the derivative in respect to theta of this guy. That's called the Fisher score. And the Fisher information equals to, I think it's a little better to write it here, like this. Actually, probably like this is better, like the double dot notation, like the second derivative, like that. And once again, why should you care about what the Fisher score and what the Fisher information is? What's really interesting is that it links together the curvature of the likelihood estimator with the parameter, right? And with the sample that you've gotten, right? So I read this analogy online, which was really interesting. And it says that, imagine that you have a statistical model on a USB, and it's got, I don't know, thousands and thousands of variables that are used to create the model. And you've only got like a finite amount of memory on your USB, right? So you need to figure out at that stage which ones are important and which ones are not important, right? Which ones do you leave out of the model so you can put everything onto this USB? And the idea is you have to calculate the Fisher information for each variable. And if the Fisher information is 0, that means that this parameter, theta, actually has no effect on the likelihood curve, right? So it's saying if the second derivative, which usually means curvature, right, when you're thinking about a function, if its expected value means that if it's like 0, then therefore it just doesn't have an effect on the likelihood estimation, which means it's not really having an effect on the model itself, right? But this would be, if this was really, really large, it means that this parameter in question really does have an effect because it's really wildly changing the curvature of the likelihood estimator, right? So I feel as if this is like a way to quickly realize which parameters are actually useful to your model, right? Here's some properties that are not too difficult, but you should just remember them just in case. The expected value of the Fisher score is 0. And the I feel as if this is exactly that. The derivative squared, it's the same thing. Just some properties that you need to remember. And I know I already used this, but you can also approximate the standard error of your MLE estimator to be 1 over the root of your Fisher information of the estimator. Okay. So we want to find the Fisher information for sigma given n equals 1. And this is the same assignment question. So this is the same, like, you know, whatever it was. 1 on n sum ln xi squared. Something like that, right? It's the same question. And so just using the same parts as before, you can calculate the second derivative, which we did, forget where. We calculated it here, right? So I'm just using that to get this value. Substitute n equals 1. We get this guy. We know that ln of x has this distribution, 0 sigma squared. And so therefore the expected value of ln x squared equals the variance of ln x squared minus expected value of ln x squared squared. That's just the definition of, where is this? Where am I using that? I believe it's this guy, right? Or I might be wrong. Oh, yeah. Apologies. Usually, the variance of x, it's the expected value of x squared minus the expected value of x all squared. But you can also calculate the expected value of x squared just by rearranging. So you've got the expected value of x squared equals to the variance of x minus plus the expected value of x all squared. That's what we're using here. Right, and then we get that the Fisher information is therefore, well, this part here, expected value of ln x squared is sigma squared. And so just applying the definition of what it means for the information, the Fisher information, just go through the algebra, it's 2 on sigma squared. Okay. Okay, beautiful. Here is something that I'm not going to go through just because I don't think it's too particularly important. And usually with these questions, I just didn't want to bash the same example over and over again. You'd have to come up with a bunch of values, so it's just going to take a while. Through the past exam I was given, I didn't have an example of this, so I didn't know where to get an example of a world confidence interval. But just going through it, you can calculate a confidence interval for the MLE of theta with, once again, this formula. And here, instead of the t distribution, we've got z 1 minus the alpha on 2. And here we've got z 1 minus the alpha on 2, which is the normal distribution, right? That's the quantile of the normal distribution. And you can, once again, you can calculate this with data given, you can calculate this with data given, and you can calculate the standard error, right? So it's just a formula, not too bad. Here's another thing, it's called the Kramer-Rowe lower bound. And it says the estimator of theta n equals just, once again, it's a function, it's a statistic, is unbiased estimator of theta, then the variance of that estimator is greater than or equal to 1 over n I1 theta. Yep, nothing to go over here. I'm actually not even too sure about the proof of this. I think it's like you have to use the mean value theorem, something like that. It's a little bit involved. It might be good to know. I think there was like 1 or 2 questions on it. Okay. We've got multi-parameter maximum likelihood inference, and I think I'll quickly show before that when we were talking about maximum likelihood inference, we specifically only had one parameter of interest. It was theta. So we can think of this as like the one variable case. Right? And so usually if you want to calculate the Fisher information, you just have to calculate the second derivative, and that tells you the curvature. Unfortunately, if we go all the way back to here, this is no longer the case when we've got multiple parameters of interest, right? If you've taken MATH2801, I think you'll realize that this awfully looks similar to the Hessian matrix, H, right? And the Hessian is what was used to calculate the curvature of multivariable functions, right? I think you have to calculate like the eigenvalues of it, something like that, and then that will tell you the curvature. You can see this like more clearly if you just take the I2 theta case, and I'm just going to omit the expected values. You get H11, H12, H21, H22, and then this is just going to be the second derivative of, let's say, theta I squared. Then there's going to be the mixed partial derivative, d theta I, d theta j, and then here's also going to be the mixed partial derivative, but just in the reverse order. Oop. Same thing here, just with the other variable. Okay, wonderful. And that's exactly the definition of the Hessian matrix. So although this formula looks like straight out of nowhere, it's just applying like the definition of the Hessian, and it's just generalization of what it means for curvature for multivariable functions, which is not too bad if you're familiar with MATH2801. Okay. Moving on, we can also have multi-parameter maximum likelihood inference, and so it's just by this formula, where the standard error is this. Not the greatest looking formula ever, and I'll just quickly remind everyone what nabla means. It just means the gradient, right? Gradient of a function, and if g of theta was just, I don't know, write this here, some multivariable function, then it's got g of theta 1 all the way up to g theta n. Probably a little better if I say that this is the g1 function of theta, the gn function of theta. And then you can just make this, and that, just the same definition, same thing. Okay. Okay, perfect. I think we can talk about hypothesis testing now. And I'll quickly just go through the definition. And the null hypothesis, labeled H0, is a claim that a parameter of interest to us theta takes a particular value theta naught, hence H naught has the form theta equals theta naught with some prescribed value theta naught, which is a very convoluted way of saying that the null hypothesis just is basically what you want to test, right? So if you think, I don't know, Dream was cheating in Minecraft or something, you'd say that H naught, the expected value of the drop rate of like blaze rods was 880, right? And the alternative hypothesis, labeled H1, is a more general hypothesis about the parameter of interest to us, right? So it can just be, it's just essentially what happens if this wasn't true? What should we accept if this isn't the case? And so, I don't know, in the dream example, perhaps he is cheating, so H1 would be the statement that his average was greater than the expected average, which is 880, right? So that's two hypotheses. If you think that dream is cheating, you say, well, the null hypothesis is that he isn't cheating. It is indeed that his average was 880. And the null hypothesis would be that his average was greater, right? And then you have to think about which hypothesis do you accept? And the question is, how do you actually perform this? How do you go through the motions of saying, how do we reject this? How do we accept this? Or whatever alternative that you do end up achieving. Okay. Cool. Here's a Mythbusters example, and they were testing whether or not toast lands butter side down more often than butter side up. In 24 trials, they found that 14 slices of bread landed butter side down, and we want to ask, is this evidence that toast lands butter side down more often than butter side up? Okay. And so I'm just going to go through the method of how you actually perform a hypothesis test. And the first step is to just state the null hypothesis and the alternative hypothesis. By convention, the null hypothesis is the more specific of the two hypotheses. So you don't want to say that H0 is like mu is not equal to C, or mu is greater than C, or mu is less than C. You want it to be some specific value. Just by convention, it doesn't really mean anything. You can just say that mu equals to C, right? That's the null hypothesis. And the alternative hypothesis is the more general claim, right? In this example, because we want to investigate if toast lands butter side down more often, we'd say that the butter side down is greater than C, right? It happens more often than what we would expect. Now we ask ourselves the question, how much evidence is there against the null hypothesis? So we need to find a test statistic that measures how far out data is from the expected null hypothesis. So essentially what this is saying is that if we accept the null hypothesis to be true, how likely is it that we could expect the data that we received? That's essentially what's being asked. And so that's what the p-value is. It's that probability. What is the probability that if the null hypothesis were true, we could get this data? From here, we can write a conclusion. Okay, so doing the Mythbusters example, I'm going to let P equal the probability that toast lands butter side down, right? Then H0 is the probability that this is a half, so it doesn't matter, right? So it happens equally likely. We'll land butter side down or butter side up, it's a half. Versus the alternative hypothesis is that it does indeed land butter side down more often, which just means greater than a half. General and specific. Okay, now we want to let p hat be the sample proportion, and in particular we'll look at the test statistic z equals p hat minus p root p1 minus p over n. And hopefully this jogs your memory of, I think it was the first example we did, of the normal approximation of a binomial distribution, right? Because this is indeed binomial, or actually probably better to say it's a Bernoulli distribution. So this is just the same as saying root n p hat minus p over root p1 minus p approaches in distribution to normal 0, 1. Okay? Move this over to the side. Okay. And so if we assume the null hypothesis to be true, then p does indeed equal to a half. And so we can just substitute that in wherever in, right? I'm not going to substitute in n equals to 24 because then we no longer have, like, it's not really approaching anything anymore if we fix n, right? So I just want to keep this statement general. So I just won't substitute in n at this point, just so I can still say that this is the case. Okay. So we need to ascertain whether our sample, which was 14 over 24, is unusually large if our null hypothesis is true. So we're asking what is the value that the data we received is greater than or equal to 14 over 24, assuming the null to be true. Okay. And so we can figure that out just by observing. So I'm just going to go through the motions of this, is that we start with this, we then subtract minus 0.5 on both sides, and then we divide out by this expression. And then all of a sudden, we get our approximate distribution, Z, on one side. So you get that probability that Z is greater than or equal to this expression. We can just substitute in n equals to 24 now. So we're asking, is Z greater than 0.082, and that's 0.2071. And I think to work this out with R, you have to write Qnorm. Correct me if I'm wrong. Or it actually might be Pnorm. It's 1 minus Pnorm of 0.82, I think. This is maybe. I forget how to do this in R. But this is just some value you can get in R. Okay? Now the question comes up is, how significant is 0.2071 as a probability? Is this like absurd? Is it not absurd? Is this something we can expect? And that comes into the question of how do we interpret these p-values? And so that is the range of a p-value and its conclusion. If the p-value is greater than or equal to 0.1, then there's little or no evidence against H0. If it's within this region, we say that there's some but inconclusive evidence of H0, and so on and so on and so on. Okay? In our case, we've got that it's 0.2071, so we're firmly in this category. Okay? So to conclude, since 0.2071 is greater than 0.1, we conclude that we have no evidence against the claim that p equals 0.5, because our data is consistent with this hypothesis. And so it is indeed that the null hypothesis we can assume to be true, right? But it's better written in this format. We don't want to say it is true, we just have no evidence against it, okay? Here's normal samples. So in the situation where these guys are mu sigma squared, we can use the fact that this guy is Tn minus 1 distributed. And we can use this to test any hypothesis of this form. Okay, so I'm going to go through an example here, which states that before the installation of new machinery, the daily yield of fertilizer produced by a chemical plant had this mean. Some new machinery is installed, and we would like to know if the new machinery is more efficient. During the first n equals 50 days of operation of the new machinery, the yield of fertilizer was recorded. The sample mean was this number here, with a standard deviation of S equals to 21. So we would like to know if this new machinery is indeed more efficient. And the way we're going to answer that question is by making a null hypothesis, well, doing a hypothesis test, okay? So here it is. This is the first method, which is method 1. I'll quickly go through something called a rejection region in the next method. And our first hypothesis is that mu equals to 880. So we're saying that it didn't have an effect, right? So this new machinery isn't really making all much of a difference versus the fact that it is indeed more efficient. We're saying mu is greater than 880. Okay? And so our test statistic is this guy, right? That's what we've written here. I'm going to make this clear and say that this is our test statistic that we should use. Okay? And so using the data given, we can say that t is greater than our average minus 880 over s root n, substitute in our values, and we're asking what is the probability that t is greater than 2.69. Okay, and then using r, we find that this probability is 0.049, which is less than 0.005. Okay, therefore, because if we go back to our p-values, we are firmly in, was it 0.05? We're somewhere here. I forget what the specific number is, but we definitely do have evidence against H0. Okay? So we're just going to write a conclusion saying this tells us that if H0 were true, we would it would be highly unlikely to observe a t-statistic as large as 2.7. Therefore, we've got strong evidence against the claim that mu equals to 880, and therefore these new machinery is actually more efficient. Okay, and this is just the first method. You can do another method called, which is basically the idea of a rejection region. And you just have to find a rejection region for a test size of 0.05, right? So what you do is you say, to determine a rejection region, you need to choose a size or a significance level for the test, and we usually use 0.05, right? So since our test statistic is T49 distributed, then we can use R to find some value C such that the probability that T is greater than Z is approximately 0.05. And that R command is this. Okay? And using that, it gives us this value. Hence our rejection region is T greater than 1.676. Okay? Because any value larger than that, then this guy's just going to get smaller and smaller. Okay? Hopefully that makes some sense. That is, if T is greater than 1.676, we'll reject H0 in favor of H1. Else, we'll retain H0. Our observed value of T was 2.69, which is in our rejection region. And to make this super clear, our rejection region pertains to the null hypothesis, right? So if it's in the rejection region, we reject H0 in favor of H1. Otherwise, we go for H0. Okay? As such, we reject H0 and conclude that there is evidence against the fact that mu is greater than 880. Okay. Does anyone have any... I kind of zoomed by this pretty quickly just because there isn't a whole lot of time. But does anyone have any questions? Okay, perfect. If no one has any questions, then I think we can end the stream here. Just final word of, advice, just make sure to do as many examples as you can. Go through the tutorial questions meticulously. I remember in my final, a lot of the final questions were like really similar to the tutorial questions. And I'm pretty sure the tutorial questions have fully worked solutions. So, yeah, make sure just to go through that. I know Donna hasn't given a whole lot of past exams. Yeah, thanks, Caroline. Sorry. Okay, perfect.